The universe began with just three simple ingredients. For hundreds of millions of years, it was a dark, swirling soup of hydrogen, helium, and a tiny trace of lithium. There were no planets, no rocks, and certainly no life, because the periodic table of the cosmos was almost entirely blank. Then came the architects of everything we know. This is the story of the first stars, the original cosmic alchemists. Their brilliant lives and violent deaths did not just light up the darkness. They performed the ultimate chemistry experiment, forging every element that would eventually build our world. By the end, you will understand how the atoms that make up your body were first created in the hearts of these stellar giants. We will trace the journey from that pristine, empty cosmos to the chemically rich universe that made planets and life possible. How did a void of simple gas become a factory for complexity? And what fingerprints of those first titans can we still find today? What does it mean that our own existence hinges on a chain of events set in motion by stars that died billions of years ago? That early cosmos was a place of profound and perfect simplicity. Picture it not as the starry night we know, but as an endless, silent fog. A deep, uniform sea of gas stretched across the entire universe, so dark you would see absolutely nothing in any direction. This was the Cosmic Dark Age, a chapter lasting hundreds of millions of years where not a single star had yet sparked into existence. The ingredients for this fog were shockingly few. Roughly 75% was hydrogen, the simplest and lightest element. The remaining quarter was helium, the next lightest, and mixed in was a ghostly trace, a mere 1 part in 10 billion, of lithium. That was it. The entire periodic table, from carbon to oxygen to iron to gold, was completely absent. The universe was chemically empty, a blank canvas waiting for its first brushstroke. This simplicity, however, created a massive problem for star birth. For a cloud of gas to collapse under its own gravity and ignite a new star, it needs to cool down. Think of it like this: a hot gas cloud is puffy and energetic, its particles bouncing around vigorously, resisting the pull of gravity. To condense into a dense, hot core, it must shed that energy, it must cool. In our modern universe, this happens efficiently because interstellar clouds contain tiny grains of dust, specks of heavier elements like silicon and carbon. These dust grains act like radiators, absorbing the cloud's heat and re-emitting it as infrared light, allowing the cloud to shrink. But in that primordial fog, there was no dust. There were no metals, as astronomers call all elements heavier than helium. The only way for that pure hydrogen and helium gas to cool was through a slow, inefficient process involving the hydrogen molecules themselves. It was like trying to chill a vast hot room with a single, tiny ice cube. The collapse was agonizingly slow, taking tens of millions of years for just one cloud to finally condense. The universe was stuck, a patient but sterile nursery, waiting for something to break the logjam and allow the first mighty seeds of light to finally take root. Yet within that uniform, silent fog, the seeds of everything to come were already present. The Big Bang did not leave behind a perfectly smooth universe. Instead, it imprinted it with the faintest of whispers, tiny ripples in the fabric of space itself. These were minute variations in density, regions where the cosmic gas was ever so slightly thicker or thinner than average. They were the universe's original blueprint, and gravity was the force that would read it. First to respond was dark matter, that mysterious substance which feels gravity but is completely invisible to light. Because it does not interact with radiation, it was free to start clumping together immediately, long before the first stars. These clumps of dark matter acted as cosmic scaffolds, creating deep gravitational wells across the darkening cosmos. Then the ordinary gas, the hydrogen and helium, began to feel the pull. Drawn inexorably toward these unseen concentrations of mass, the gas started to flow. It streamed into the wells, piling up to form vast, diffuse clouds that spanned hundreds of light years. These were the first true structures in the universe, the primordial cradles for starlight. But even within these massive clouds, the process was slow. The gas was still hot and had no efficient way to cool. It swirled and churned in the darkness, a chaotic ballet governed by gravity's patient hand. Only in the very deepest, densest cores of these clouds did conditions finally become extreme enough. Here, the weight of the gas became overwhelming. Under unimaginable pressure, the collapse into a true protostar began. It was not a sudden ignition, but a long, arduous squeeze, a gathering of potential that would take millions of years to reach its climax. The stage was finally set, and in the heart of that crushing darkness, the first spark was about to be born. From this long, slow squeeze, a new kind of star finally ignited. Astronomers call them population 3 stars, and they were unlike anything that has existed since. They were the true pioneers, forged from that pristine, metal-free gas. Their defining trait was sheer, unimaginable scale. While our own Sun is a stable, middleweight star, these firstborns were cosmic titans. They likely formed with masses ranging from tens to possibly hundreds of times that of our Sun. The reason for their monstrous size lies in that very simplicity we discussed. With no heavy elements to form dust and cool efficiently, the collapsing gas clouds could only fragment into enormous clumps. There was a minimum mass required to trigger the final collapse, and that minimum was staggeringly high. You could think of it like trying to make a snowball from perfectly dry, fluffy snow. You need a huge amount of it to finally pack into a dense, solid core. So the first stars were not just big, they were almost exclusively super-sized. This purity of composition meant their entire existence was a radical experiment. Burning only hydrogen and helium in their cores, their internal physics ran hotter and faster. They lived lives of incredible intensity, pouring out torrents of ultraviolet light into the surrounding darkness. But with great mass comes a dramatically shortened lifespan. Where a star like our Sun will shine for billions of years, these giants burned through their nuclear fuel in a mere few million. Their brilliant, brief lives were a prelude to an even more transformative event, one that would forever shatter the chemical simplicity of the cosmos. Deep within that crushing core, a new kind of fire was born. The relentless gravitational squeeze raised temperatures to unimaginable heights, surpassing 10 million degrees. At this critical threshold, a fundamental barrier was broken. The protons at the heart of hydrogen nuclei, which normally repel each other due to their positive charges, were forced together with such immense pressure and heat that they fused. This moment, the ignition of sustained nuclear fusion, marked the true birth of the first star. The outward rush of energy generated by this process finally halted the gravitational collapse, creating a fragile, radiant balance that would define its life. The star began to shine, not with chemical fire, but with the light of atomic transformation. The primary engine for this in most stars, including our Sun, is called the Proton-Proton chain. It is a step-by-step process where hydrogen nuclei are fused, eventually creating helium and releasing energy. But for massive stars, there is a far more powerful and efficient pathway called the CNO cycle. This cycle uses carbon, nitrogen, and oxygen as catalysts to speed up hydrogen fusion dramatically. Here lies the first star's unique and profound challenge. These stars were forged from pure hydrogen and helium. There was no carbon, there was no nitrogen, there was no oxygen. The very catalysts required for the CNO cycle did not yet exist in the universe. So, at the moment of their birth, these titans were forced to rely solely on the slower, less efficient proton-proton chain to compensate and produce enough outward pressure to support their staggering mass. Their cores had to become even hotter and denser than usual. Think of it like trying to power a massive freight train with a small, high-revving engine. You have to run the engine at a furious, unsustainable rate just to get moving. This is what happened inside the first stars. Their fusion furnaces roared at an extreme pitch from the very beginning, burning through their pristine hydrogen fuel at a breathtaking, prodigal rate. This furious start dictated their entire destiny, guaranteeing that their brilliant light would shine for only a cosmic instant, a few fleeting million years before the fuel ran out and the core faced its inevitable, world-altering fate. This furious burning set the stage for the universe's first chemistry lab. Deep within the star's core, the initial hydrogen fuel began to dwindle. As the hydrogen fused into helium, this helium ash started to accumulate at the very center. With less hydrogen fusion to push outward, gravity gained the upper hand once more, and the core began to contract. This contraction, however, raised the temperature and pressure to even more staggering extremes, reaching over 100 million degrees. At this new threshold, a second chapter of creation began. The helium nuclei, which had been the waste product of the first fire, themselves became the new fuel. This is where the story of our own atomic origins truly starts. Under these hellish new conditions, two helium nuclei could now fuse to form a highly unstable form of beryllium. This beryllium isotope lasts for only a fleeting fraction of a second before it decays, but in that unimaginably hot, dense core, something miraculous happened. Before that beryllium could fall apart, a third helium nucleus slammed into it. In a 1 in a trillion cosmic collision that had never before occurred in the universe, the three helium nuclei fused together. The product of that triple merger was a single, stable nucleus of carbon. In that instant, for the very first time since the Big Bang, an atom heavier than lithium was born. The universe had just forged its very first piece of solid matter, the foundational element for all future organic chemistry and life itself. With carbon now present, the star's internal engine shifted into a higher, more complex gear. The core, now rich with this new element, could temporarily find a new balance, but the star's immense mass meant this stability was brief. Once again, the helium fuel would run low, the core would contract, and temperatures would soar even higher. At around 200 million degrees, a new reaction became possible. An additional helium nucleus could now fuse with that newly minted carbon atom. This process, called alpha capture, added 2 protons and 2 neutrons, transforming the carbon into a nucleus of oxygen. This was not a one-time event, but a relentless, layered chain of creation. As each fuel source was exhausted, the core compressed and heated, unlocking the next fusion step. Oxygen could capture another helium nucleus to become neon. Neon could capture helium to form magnesium. This stepwise addition, building elements like a cosmic bricklayer, proceeded through silicon and sulfur, all the way up to iron. The star was no longer a simple ball of fire. It was becoming a layered onion of elements. At its very center sat an iron core, surrounded by concentric shells of silicon and sulfur, then magnesium and neon, then oxygen, carbon, helium, and finally an outer envelope of the original hydrogen. This entire process, the forging of heavy elements inside a star, is what astronomers call stellar nucleosynthesis. And in this first generation of giants, it was running for the very first time in all of cosmic history. Every atom of carbon in your body, every breath of oxygen you take, every piece of rock and metal on Earth, traces its original lineage back to this precise sequence of reactions blazing inside those ancient, vanished titans. They were not just lights in the dark, they were the universe's first and most critical factories, transforming primordial simplicity into the raw materials for everything to come. But this layered creation had a fundamental and fatal limit. The process of building heavier elements through fusion is not a limitless source of energy. In fact, with each new step up the periodic table, the star gains less and less power from the process. Fusing hydrogen into helium releases a tremendous amount of energy, which is why stars can shine for so long. Fusing helium into carbon releases less energy per reaction. Carbon into oxygen releases less still. Each successive stage, from oxygen to neon, neon to magnesium, and so on, provides a diminishing return. To compensate and keep gravity at bay, the core must burn through each new fuel source faster and faster. The star's life becomes a frantic, accelerating sprint. The hydrogen burning stage might last millions of years. Helium fusion may last only a few 100,000. The carbon burning stage could be over in a mere 1,000 years. By the time silicon begins fusing into iron, the core is racing through its final fuel supply in a matter of days. This is why we picture the star's interior as a layered onion. At the very end, the core is not a uniform mix, but a set of nested shells, each fusing a different element, all burning at a different, ever-quickening pace. And at the very center of it all, a silent, inert mass begins to grow, the ash of the final fusion stage, the element iron. Iron is the end of the line for stellar fusion. This is the most critical chemical fact in our cosmic story. For all elements lighter than iron, fusing them together releases energy, which creates the outward pressure that holds the star up. But iron is different. Its nucleus is the most tightly bound of all. Trying to fuse two iron atoms does not release energy, it consumes it. It is like trying to start a fire by pouring water on the logs. The moment the silicon shell finishes its work and deposits its final ash into the core, the star's central engine simply stops. No new energy is generated. For eons, that relentless outward push from fusion had been the only thing fighting the star's own immense weight. Now that support vanishes instantly. The core, now a ball of iron roughly the size of Earth but containing more mass than our Sun, finds itself in a catastrophic predicament. With no fusion to hold it up, nothing can stop the crush of gravity. The entire outer mass of the star, all those layered shells of oxygen, carbon, and helium, begins a free-fall collapse toward the dead iron center. This is the ticking time bomb, the final, unstoppable countdown. In less than a second, the core is compressed to unimaginable densities, triggering a violent and paradoxical rebound. That rebound will not just destroy the star, it will unleash forces so extreme that they accomplish what the star's core could not, forging every single element heavier than iron and scattering them across the cosmos. The star's work as a contained factory is over. Its final, most important role is about to begin, as it prepares to seed the universe with the full palette of chemistry. The star's final moment arrives not with a whimper but with a silence. When the last of the silicon fuel fuses into iron, the core's nuclear furnace simply goes dark. For millions of years, a delicate balance had held, the outward push of fusion perfectly countering the inward crush of gravity. That balance is now shattered. With no energy being generated at its heart, the iron core has nothing left to support its own immense weight. It begins to collapse under its own gravity, and nothing in the universe can stop it. In less than a single second, a core the size of Earth is compressed into a sphere barely 20 miles across. The density becomes so extreme that protons and electrons are forced together, merging to form neutrons and releasing a flood of ghostly particles called neutrinos. This sudden transformation creates a brief, final moment of resistance. The collapse halts, and the core stiffens into an ultra-dense neutron star. But the outer layers of the star, all that oxygen, carbon, and helium, are still in free fall, plummeting inward at nearly a quarter the speed of light. They slam into this newly formed, incredibly hard surface. The impact is catastrophic. The infalling material rebounds violently, creating a shockwave of inconceivable power that races back outward through the star. This is the supernova. The energy released in this single event can outshine an entire galaxy of stars. For a few glorious weeks, this one dying titan becomes the brightest object in the young universe. But its true legacy is not the light, it is the chemistry. The supernova explosion is the universe's ultimate delivery service. The shockwave tears the star apart, blasting its entire layered structure out into the surrounding void. The outer layers, rich with the elements forged during the star's life, are hurled into space at thousands of miles per second. This cosmic debris cloud, now expanding for light years, contains all the carbon, oxygen, neon, magnesium, and silicon created in the star's onion-like interior. Yet the supernova's role goes beyond mere distribution. It also provides the final, extreme conditions needed to finish the periodic table. The temperatures and pressures in the rebounding shockwave itself are even more ferocious than the star's core at its peak. In this maelstrom, a frantic, chaotic process called explosive nucleosynthesis takes place. Atomic nuclei are bombarded by a dense hail of neutrons, allowing them to rapidly capture these particles and climb the ladder of elements in minutes instead of millions of years. This is how every element heavier than iron is born. Gold, silver, platinum, uranium, all the metals that make up our planets and our technology are forged in these few, fleeting moments of stellar death. In one magnificent, violent act, the first star accomplishes its ultimate purpose. It scatters the seeds of complexity far and wide, enriching the pristine cosmic gas with the very ingredients for rocky planets, oceans, and eventually life. The chemical universe is no longer a theory, it is a reality painted across the darkness by the death of a giant. The supernova's fury creates the ultimate forge for the heaviest metals. While the star's core fusion built elements up to iron, the final cataclysmic explosion builds everything beyond it. This happens through a frantic, almost magical mechanism known as the rapid neutron capture process, or the Are process for short. Picture it like this: in the unimaginably hot, dense debris of the exploding star, a blizzard of free neutrons is unleashed. These neutrons, particles with no electrical charge, are the key building blocks. Nearby atomic nuclei, the seed elements like iron forged earlier, are caught in this storm. Normally, if a nucleus captures a single neutron, it becomes unstable and might quickly decay, transforming a neutron into a proton and effectively stepping just one place up the periodic table. But in the Are process, conditions are so extreme that the capture happens far, far faster than the decay. Nuclei are bombarded, capturing neutrons one after another in rapid succession before they have any chance to stabilize. It is a frantic race up the weight scale. A single iron seed nucleus can gulp down dozens of neutrons in a matter of seconds, becoming incredibly heavy and unstable. Only after this explosive neutron-feeding frenzy ends, as the expanding cloud cools and thins, do these super-loaded nuclei finally begin to decay. They shed neutrons and convert them to protons step by step, sliding down into stability. This decay chain is what plants them firmly as brand new, stable heavy elements on the periodic table. Gold, platinum, uranium, all the elements we mine from the Earth for jewelry, technology, and energy are born from this precise, violent sequence. The Are process is the universe's way of finishing the job that stellar fusion started. Core fusion built the architectural framework of the cosmos, the carbon, oxygen, and iron. But the Are process, powered by stellar death, provided the final, intricate decoration, the dense, rare metals that add complexity and possibility. It was the final gift of those first stars, ensuring their legacy was not just a few light elements, but the entire chemical palette needed for a rich and varied universe. The explosion's echo fades, but its work has only just begun. Scattered across light years of space, the shattered remains of that first star now drift as a vast, expanding cloud of cosmic ash. This debris is no longer just hydrogen and helium. It is a rich chemical soup laced with carbon, oxygen, iron, and even traces of gold. Astronomers have a simple, powerful word for all these newly forged elements. They call them metals. To them, any atom heavier than helium is a metal, the building block of solid things. This cloud of metallic ash now begins its most crucial journey, drifting through the pristine sea of primordial gas that still fills the universe. The process is slow and majestic, like a single drop of ink dispersing in a still pool of water. At first, the heavy elements are concentrated in a dense knot. But over millions of years, turbulence and the sheer expansion of space itself stir the mixture. The metals gradually diffuse, blending with the surrounding hydrogen and helium. They do not disappear, they become a faint but permanent spice, seasoning the entire region. Where once there was only simplicity, there is now a subtle, foundational contamination. This is the universe's first and most vital act of pollution. The pure gas clouds from which the first stars formed are gone forever, transformed into something new, second-generation material. These enriched clouds now contain the seeds of everything to come. That trace of carbon can form dust grains. Those specks of silicon and iron can clump into microscopic rocks. This changes everything about how the universe builds its next structures. When gravity once again begins to pull on these enriched clouds, the process of star formation is utterly transformed. Those tiny dust grains act like millions of microscopic radiators, allowing the gas to cool far more efficiently than pure hydrogen ever could. Cooler gas can collapse into denser, smaller clumps. This means the next generation of stars will not all be monstrous giants. They can form with a wide range of sizes, from small, long-lived red dwarfs to stars like our own sun. The chemistry forged in death directly dictates the diversity of life that follows. Furthermore, this enriched gas is stickier. When particles collide in space, they often just bounce apart. But if they are coated with water ice or complex carbon molecules, things that can only form with heavy elements, they can stick together like cosmic snowballs. This is the very beginning of planet building. Without that first stellar pollution, gas clouds could only fragment into enormous stars. With it, they can fragment into solar systems. The death of those first titans did not just create the elements for planets, it created the very conditions that allow planets to form at all. The universe had crossed a fundamental threshold from a place that could only make stars to a place that could make worlds. The universe was no longer chemically sterile. That faint metallic seasoning scattered by ancient supernova acted as a cosmic catalyst, triggering a revolution in how stars themselves were born. The key lies in a simple but profound principle: cooling. To collapse into a star, a gas cloud must shed its heat. In the primordial era, pure hydrogen and helium could only cool slowly, forcing clouds to stay large and puffy, which is why the first stars were all giants. But now the gas contained new players, atoms of carbon, oxygen, silicon, and iron. These heavier elements are far more efficient at radiating away heat. They act like a network of microscopic radiators embedded throughout the cloud. As the gas begins to contract, these atoms get excited and release that energy as infrared light, allowing the cloud to shrink and grow denser much faster. This efficient cooling changes the entire fragmentation process. Instead of a massive cloud collapsing into one or two enormous clumps, it can now splinter. It breaks apart into numerous smaller, denser knots of gas, each one a potential seed for a new star. This is how the universe went from crafting only solo titans to building entire families of stars. From these enriched clouds, a new stellar generation emerged. Astronomers call them population 2 stars. They were fundamentally different from their colossal ancestors. With the ability to fragment, they formed across a wide spectrum of sizes, from stars many times the mass of our Sun down to small, dim red dwarfs. Their most defining feature, however, was written in their light. For the first time, starlight carried the faint spectral fingerprints of heavy elements. These population 2 stars were not pure. They contained trace amounts of metals, perhaps only 1/10,000th the metal content of our Sun, but it was there. This was the direct chemical inheritance from the first stars. Every atom of carbon or oxygen in their atmospheres was recycled debris, the ashes of those long-dead pioneers, now incorporated into a new celestial body. This marked a profound transition in cosmic history. The universe was no longer a place of isolated, brilliant flashes that lived fast and died young. It could now sustain a diverse stellar population, with stars of varied masses, colors, and lifetimes. The small red dwarfs born in this era, for instance, are so fuel-efficient that they can shine for trillions of years, outliving the current age of the universe itself. This shift from a monolithic to a diverse stellar ecosystem was only possible because of that initial chemical pollution. The death of the first stars did not just create the ingredients for planets, it created the conditions for stable, long-term galactic neighborhoods where complex cosmic evolution could truly begin. But for the most extreme giants, a far more spectacular fate awaited. Among that first generation of stars, the true behemoths, those with masses soaring above perhaps 130 times that of our Sun, may have met their end through a mechanism of pure cosmic overkill. Astronomers call this a pair-instability supernova, and it represents a different kind of stellar death, one so utterly complete that not even a neutron star remains. The trigger lies in the star's own ferocious heat. In its final days, as the core contracts under the weight of its outer layers, temperatures can climb to truly staggering heights, exceeding 1 billion degrees. At this extreme, the photons of light, or gamma rays, buzzing around the core are no longer just carriers of energy. They become raw material. They possess so much energy that when 2 of them collide, they can spontaneously transform into a pair of particles, an electron and its antimatter counterpart, a positron. This transformation is the key to the catastrophe. Those gamma-ray photons were providing radiation pressure, an outward push helping to support the star. By converting into matter, that pressure suddenly vanishes. It is as if the supporting pillars of a vast building instantly turn to dust. The core, robbed of its crucial support, experiences a sudden and catastrophic loss of pressure. Gravity wins in an instant. The collapse that follows is not a controlled fall, but a runaway implosion of unimaginable violence. The entire core plunges inward at nearly the speed of light. This implosion, however, does not end with a rebound against a hard neutron star surface. Instead, the infalling material becomes so hot and dense that a new wave of nuclear fusion ignites explosively throughout the collapsing core. It is a final, total fusion blast. The energy released is so titanic that it does not just halt the collapse, it completely overwhelms the star's gravity. In a single, apocalyptic instant, the entire star is utterly annihilated. No black hole, no neutron star, not even a wisp of a remnant is left behind. The star is completely vaporized, its entire mass converted into an expanding fireball of newly forged elements and raw energy. This complete disruption has a profound chemical consequence. Because the entire star is fused and blasted apart, pair-instability supernova are predicted to be phenomenal factories for specific lighter elements, particularly oxygen and silicon. They take the pristine helium from the early universe and, in one final, all-consuming furnace, transform it into vast quantities of these critical building blocks. The chemical signature they leave behind in the gas they enrich would be distinct, a potential fingerprint of these first and most monstrous stars. Their existence, though still largely theoretical, helps explain how the earliest galaxies might have been seeded with such a rich and specific mix of elements, setting the stage for the complex cosmic chemistry that would follow. The story so far is a grand cosmic theory, a narrative pieced together from fundamental physics. But how can we be sure it actually happened? The answer lies not in distant galaxies, but surprisingly in our own cosmic backyard. Scattered throughout the vast halo of the Milky Way, astronomers have discovered a handful of incredibly ancient stars. These are not the bright, familiar stars of the galactic disk, but faint, aging relics that have been orbiting our galaxy for over 13 billion years. They are the surviving witnesses to that primordial era, and they carry a chemical memory locked within their light. By analyzing the specific colors or spectrum of that starlight, scientists can perform a kind of cosmic forensics. Each element absorbs light at very specific wavelengths, creating unique dark lines in the star's spectrum, like a barcode. Reading this barcode reveals the star's exact chemical composition. What they find in these ancient stars is astonishingly simple and profoundly telling. They are what astronomers term extremely metal-poor stars. Their atmospheres contain only the tiniest traces of elements heavier than helium, sometimes just 1/10,000,000th the metal content of our Sun. This extreme purity marks them as second-generation stars, formed from gas that was only lightly polluted by the very first supernova. They are the direct descendants of the population 3 era. One of the most famous examples is a star with the catalog name SMSS J0313-6708. Its light, which has traveled for over 13 billion years to reach us, tells a particularly stark story. The analysis shows a bizarre and revealing chemical fingerprint. This ancient star is rich in carbon, yet it contains almost no iron at all. The iron level is at least 1,000,000 times lower than in our Sun. This pattern is not what you would expect from gas enriched by many different supernovae over time, which would create a more blended, uniform mix. Instead, it points to something far more specific. This star appears to have formed from a cloud of gas that was polluted by just one single supernova explosion from one single first star. The chemical signature is a direct fossil of that one event. The high carbon suggests the supernova was likely from a moderately massive first star, one that produced and ejected plenty of carbon. The near absence of iron tells us the explosion was likely a faint supernova, where the shockwave did not fully escape the core, leaving much of the newly forged iron trapped behind, perhaps in a black hole. Only the outer layers, rich in lighter elements like carbon, were expelled to seed the next generation. Each of these ancient stellar relics tells a similar, yet uniquely detailed story. Their elemental abundances are not random. They are precise records like cosmic ledger entries, detailing the mass, life, and explosive death of individual population 3 stars. By collecting these stellar fossils, astronomers are slowly assembling a family album of the universe's original giants, reading the chemistry they left behind to reconstruct the very first chapters of cosmic history. These ancient stellar fossils provide a powerful but indirect glimpse into the past. To truly witness the era of the first stars, we need to look back in time, directly into the cosmic dawn itself. This is the ultimate observational challenge in modern astronomy. The very first stars ignited over 13 billion years ago. Their light has been traveling toward us ever since, but the universe's relentless expansion has stretched that primordial light tremendously. What began as brilliant ultraviolet radiation from a hot, massive star has been redshifted, stretched all the way into the infrared part of the spectrum by its long journey across an expanding cosmos. These objects are not just incredibly far away, they are also incredibly faint, buried in the noise of an infant universe. For decades, they existed only as theoretical ghosts beyond the reach of any telescope. That is now changing. The hunt for direct evidence has entered a new era with the launch of the James Webb Space Telescope. With its enormous gold-coated mirror and suite of infrared instruments, Webb is a time machine designed specifically to peer into this elusive epoch. It is not necessarily looking for the pinpoint light of an individual first star, though that remains a tantalizing possibility. Instead, astronomers are using it to search for the collective signature of their presence. They scan the deepest, oldest parts of the sky, seeking the earliest galaxies. These are not grand spirals like our Milky Way, but small, clumpy assemblages of stars that formed from gas enriched by those first supernovae. By analyzing the infrared light from these infant galaxies, Webb can detect the chemical fingerprints in their glow, finding galaxies that show only the barest traces of heavy elements, or a strange, lopsided chemical composition like that of the ancient halo stars, would be a direct window into an environment sculpted by the very first generation. There is another, more dramatic signal astronomers hope to catch, a cosmic flash in the dark. The supernova that ended the lives of those first titans would have been spectacular events. If Webb is pointed at the right patch of sky at the right moment, it might witness the infrared afterglow of a pair-instability supernova from the universe's first billion years. Such a transient event would shine with a specific brightness and fade in a specific way, a beacon from the age of giants. Each observation is a piece of a puzzle, moving us from theoretical models toward confirmed history. The data now streaming back is not just a catalogue of distant objects, it is a chemical census of creation's first chapters, offering us a chance to finally see the shadows of the architects who built our material world. This chemical enrichment did not just create new stars, it fundamentally reshaped the architecture of the cosmos itself. The heavy elements forged by the first stars became the invisible architects of the first galaxies. Before this, the vast clouds of pristine hydrogen and helium were sluggish and inefficient, struggling to cool and collapse into anything but the most massive stellar giants. But now, with even a trace of metals present, everything changed. Those heavier atoms, like oxygen and carbon, are far more efficient at radiating away heat as infrared light. This allowed giant molecular clouds to shed their energy, cool down dramatically, and fragment into countless smaller, denser clumps. Star formation was no longer a rare, monumental event. It became a widespread, efficient process. Where a primordial cloud might have birthed a single colossal star, an enriched cloud could spawn an entire stellar nursery of thousands all at once. This sudden burst of efficient star birth is what allowed the first true galaxies to rapidly assemble their mass and light. The universe moved from a sparse scattering of brilliant beacons to dense, glowing cities of stars, and it was the chemical pollution from earlier generations that provided the blueprint. Beyond cooling, these newly minted metals performed another critical role. They built the universe's first dust. In the expanding debris of supernova and in the outer atmospheres of aging stars, atoms like carbon, silicon, and iron could clump together into microscopic solid particles smaller than a wavelength of light. This cosmic dust, seemingly insignificant, became a powerful new force in galactic evolution. These tiny grains act as protective shields. Within dense clouds, they block harsh ultraviolet radiation from young, hot stars, preventing that radiation from tearing apart fragile molecules. In this shadowy environment, simple molecules like molecular hydrogen can form and survive on the surfaces of the dust grains themselves. Molecular hydrogen is the primary fuel for star formation in the modern universe, and dust made its existence possible. Furthermore, the dust grains continue the cooling process even more effectively than atoms alone, accelerating the collapse of gas into new stellar seeds. A galaxy was no longer just a collection of stars. It was becoming a complex ecosystem with a life cycle governed by this cycle of creation, death, and recycling. This established a self-sustaining engine for cosmic evolution. A simple, three-step cycle began to turn, driving galaxies toward greater chemical complexity and structural richness. First, a cloud of enriched gas collapses to form a new generation of stars. Those stars live their lives, fusing hydrogen and helium into heavier elements in their cores. Then, the most massive of these stars die in supernova, or through stellar winds in longer-lived stars, returning those newly forged metals back into the surrounding gas. This enriched gas, now peppered with even more heavy elements and dust, cools even more efficiently, collapses again, and forms the next round of stars, which will be slightly more metal-rich than their predecessors. With each turn of this cycle, the galactic gas becomes more chemically complex. This is why younger stars, like our Sun, contain a much higher abundance of iron and other heavy elements than those ancient survivors in the galactic halo. The galaxy was literally enriching itself, batch by batch, generation by generation. This cycle did not just change chemistry, it changed structure. The efficient formation of many smaller stars, rather than a few giants, allowed for stable, long-lived stellar populations. The accumulation of metals and dust paved the way for the eventual formation of rocky planets in the habitable zones of these stable stars. The death of the first stars ignited a process that would, over billions of years, transform simple clouds of gas into the diverse, structured, and chemically rich galaxies we see today, setting the physical stage for the eventual rise of worlds like our own. The universe had finally gathered the raw materials for a new kind of construction project. All that enriched gas, now swirling with carbon, oxygen, silicon, and iron, held the potential for more than just new stars. When a cloud like this collapsed under gravity, it did not always form a single star at its center. Often, it flattened into a vast, spinning disk, a protoplanetary disk, with a young star blazing in the middle, and the rest of the material spread out in a broad, dusty pancake. This is where the cosmic chemistry experiment became tangible, where stardust literally turned into worlds. The microscopic grains of dust suspended in that disk were not abstract. They were tiny crystals of silicates, the same minerals that make up Earth's rocks, and specks of carbon compounds, the soot of ancient stellar furnaces. These were the solid seeds of future planets, and every single one was made of an atom forged in the heart of a star that lived and died long before our Sun was born. This process of planet building is a gentle, gradual accumulation. Within the disk, these dust grains begin to stick together, colliding and forming ever larger clumps, from pebbles to boulders to mountain-sized planetesimals. Gravity then takes over, pulling these bodies together into protoplanets. But the type of planet that forms depends entirely on what materials are available at its location in the disk. Close to the hot young star, only materials with high melting points can remain solid, things like iron and silicates. These become the building blocks for rocky, terrestrial planets like Mercury, Venus, Earth, and Mars. Farther out, where temperatures are lower, volatile compounds like water, ammonia, and methane can freeze into icy grains. These ices join the dust, creating much larger planetary cores that can then go on to capture massive envelopes of hydrogen and helium gas, becoming gas giants like Jupiter and Saturn. Now consider the profound implication of this. Without those heavy elements, the metals, the rocks, the ices forged and scattered by earlier stellar generations, a protoplanetary disk would contain nothing but hydrogen and helium gas. There would be no dust grains to stick together, no solid seeds to begin the process. Gravity could still act on the gas, potentially forming gas giants if conditions were just right, but it could never, ever form a rocky world. No Earth, no Mars, no place with a solid surface upon which oceans could pool or life could take root. The transition from a universe that could only make stars to one capable of making terrestrial planets is a direct and non-negotiable consequence of those first stellar cycles. Our planet, with its iron core and rocky mantle, is quite literally a collection of recycled stardust, assembled from the legacy of countless ancient stars. The chemistry that began in the hearts of the first giants provided the very mortar and brick for our cosmic home. Rocky planets were just the first physical stage. The true potential of this stellar chemistry lay in what those elements could now build together. Carbon, oxygen, nitrogen, and phosphorus, each forged in separate stellar processes and scattered across the galaxy, are the four fundamental cornerstones of organic chemistry. This is the chemistry of life itself. Their unique atomic structures allow them to link together in an astonishing variety of stable, complex chains and rings, forming the backbone of every biological molecule we know. But for these atoms to become the precursors of life, they first had to find each other in the vast emptiness of space. This is where the cosmic delivery system, now enriched with stardust, performed its next act of assembly. Within the cold, dark interiors of giant molecular clouds, those drifting atoms finally had a place to meet. They settled onto the surfaces of microscopic dust grains, the very same grains that helped form stars and planets. These frigid, solid particles acted as cosmic meeting rooms and laboratories. On their frigid surfaces, a slow-motion dance began. A wandering carbon atom might stick to a grain. An oxygen atom drifting by could attach to it. With the help of a little ambient energy, perhaps from a stray cosmic ray, they could bond, forming a simple molecule like carbon monoxide. This process, known as surface chemistry, is how the cold clouds of interstellar space became factories for molecular complexity. Water ice, a simple combination of hydrogen and oxygen, coats countless grains. Ammonia from nitrogen and hydrogen forms there too. Even methanol, a molecule that contains carbon, hydrogen, and oxygen, has been detected in abundance in these stellar nurseries. These are not yet the molecules of life, but they are its direct and essential precursors. They are the alphabet from which more complex sentences of chemistry will later be written. When a new star system forms from such a cloud, these ices and organic molecules are not left behind. They are incorporated into the swirling protoplanetary disk. Some of the water ice coats dust grains in the cooler outer regions, eventually becoming part of comets. Other, more complex molecules hitch a ride on asteroids and meteoroids. This means the chemical groundwork for biology was laid not on the young planets, but long before, in the dark, cold clouds between the stars. The first stars, by creating the essential elements and enabling the dust grains upon which they could assemble, set in motion an inexorable chemical pathway. They transformed the universe from a place that could only forge atoms into one that could link them into the molecular seeds of future complexity. The journey from stellar nucleosynthesis to a prebiotic soup on a young, rocky world was now, for the first time in cosmic history, a chemical possibility. The early cosmic sea was no longer a uniform expanse. Before the first stars, the universe was chemically identical in every direction, a perfect symmetry of hydrogen and helium. Their explosive death shattered that pristine uniformity forever. Each supernova acted as a single, isolated brushstroke of color on a vast gray canvas, but no two strokes were exactly alike. A star that died in a faint supernova might leave behind a local bubble rich in carbon but poor in iron. A titan that met its end in a pair-instability blast could flood its neighborhood with extraordinary amounts of oxygen and silicon. Another region might be seeded by the combined debris of several smaller stars, creating a more blended, balanced chemical mix. The result was a new cosmic reality, a patchwork quilt of enrichment. For the first time, one part of the universe could have a fundamentally different elemental composition than another part, just a few hundred light years away. This was the birth of true chemical diversity in the cosmos. This patchwork directly dictated the character of the second generation of stars. A cloud enriched by a single, carbon-rich supernova would form stars with that specific, odd fingerprint we see in ancient stellar fossils. A region that pooled the ejecta from many different stellar deaths would produce stars with a more familiar, well-rounded chemistry. This is why, even among the oldest stars we find today, no two have exactly the same chemical signature. Each is a unique historical document, recording the specific conditions of the local gas cloud from which it formed billions of years ago. This diversity scaled up to shape entire galaxies. A primordial galaxy that formed in a region dominated by the violent deaths of the very first, most massive stars would have been rapidly flooded with heavy elements, allowing it to build its stellar population quickly and efficiently. Another galaxy, perhaps in a more isolated pocket, might have had to wait longer for enough supernova debris to accumulate, starting its star formation later and with a different initial chemical palette. The first stars broke the symmetry of the early cosmos not with a single decree, but with a symphony of different explosions. They initiated a grand and uneven chemical evolution, ensuring that the universe that followed would be a place of variation and local history. From that initial patchwork of enrichment sprang all the stellar and galactic diversity we observe today, a direct legacy of the chaotic, creative deaths of the original architects. Yet for all we have pieced together, this story remains incomplete. The era of the first stars is a frontier, and like any frontier, it is mapped with as many questions as answers. Our understanding is built on a foundation of elegant theory and compelling but indirect evidence. This leaves profound gaps in our cosmic origin story, and these gaps are precisely what drive astronomers to build ever more powerful telescopes and run ever more complex simulations. One of the most basic questions is also one of the hardest to answer. What did a population 3 star actually look like? More specifically, what was its exact mass? Did they form exclusively as solitary giants of 100 solar masses or more? Or was there a wider spectrum, perhaps including stars as small as 10 or 20 times the mass of our Sun? The answer reshapes the entire narrative. If they were all behemoths, their pair-instability supernova would have flooded the early cosmos with specific elements like oxygen. If a range of sizes existed, the chemical enrichment would have been more varied from the very beginning. Our models of cloud collapse without metals suggest a preference for large masses, but nature has a way of surprising us. Could some of these first stars have even been born in pairs or small clusters, orbiting each other in the darkness? The dynamics of such binary systems would dramatically alter their life cycles and their final explosive deaths, adding another layer of complexity to the seeding of the first elements. Then there is the question of the enrichment mechanism itself. We have focused on supernova, but they were not the only cosmic forges. When 2 ultra-dense neutron stars spiral together and merge, they are thought to be a primary source for the very heaviest elements like gold and platinum through the rapid neutron capture process. Did these mergers play any significant role in the very first few 100 million years? Or did the universe have to wait for later generations of stars to produce the neutron stars that would eventually collide? The relative importance of core collapse supernova, pair-instability supernova, and neutron star mergers in painting the first chemical strokes is a major open puzzle. Each leaves a different elemental fingerprint in the gas it enriches. Even the act of enrichment itself is not straightforward. The blast wave from a supernova is not merely a delivery service, it is a transformative event for its surroundings. That wave of unimaginable energy can slam into nearby gas clouds, compressing them and actually triggering the birth of the next generation of stars. But it can also be so violent that it heats and disperses the gas, blowing it away and shutting down star formation in that region for millions of years. Did the first supernova primarily act as midwives or as suppressors? The answer determines how quickly and efficiently the first galaxies could assemble themselves from the ashes of their predecessors. These are not just academic curiosities, they are the guiding lights for modern research. Every new observation with telescopes like the James Webb Space Telescope is an attempt to find data that can answer one of these questions. Every sophisticated computer simulation that models the collapse of a primordial cloud is testing a different hypothesis about that initial mass range. The story of the first stars is still being written, with each discovery adding a new sentence, or sometimes rewriting a whole paragraph in our grand history of cosmic chemistry. These lingering questions cannot be answered by observation alone, but we are not powerless to explore them. We have built a virtual universe inside our most powerful supercomputers, a digital time machine to rewind the cosmos back to its very first moments. This is the world of cosmological simulations, where scientists attempt to recreate the entire cosmic dawn from first principles. The process begins with the same faint density ripples imprinted by the Big Bang, the universe's original blueprint. Into this digital void, the laws of physics are programmed with exquisite care. Gravity, the great sculptor, is modeled to pull matter together. Hydrodynamics, the complex dance of gas under pressure and heat, is calculated at every point. Most crucially, the chemistry of creation is coded in, tracking how hydrogen and helium cool, how nuclear fusion ignites, and how supernova blast newly forged elements back into the void. The simulation is then set in motion, and time, compressed from millions of years to mere days of computation, begins to flow. We watch as dark matter weaves its invisible web, as pristine gas flows into its filaments, and as the first dense knots of matter begin to glow. These are not simple animations, they are rigorous mathematical experiments that test our deepest theories against the ultimate laboratory of reality. They allow us to ask what if. What if the first stars were all above 100 solar masses? The simulation runs and shows us the chemical signature their pair-instability supernova would leave behind. What if some were smaller, dying in quieter explosions? The simulation reveals a different elemental pattern in the next generation of stars. By comparing these virtual outcomes to the real chemical fossils we find in ancient stars, we can see which theoretical pathways actually lead to the universe we inhabit. These simulations also make specific, testable predictions for what our newest telescopes should see. They predict, for example, the precise brightness and color over time of a pair-instability supernova occurring in the early universe, a beacon for instruments like the James Webb Space Telescope to hunt. They forecast what the collective light from the very first galaxies should look like in infrared data, and what strange chemical abundances might be present within them. When Webb sends back its torrent of data from the edge of time, it is not being compared just to simple ideas, but to the rich, detailed virtual universes generated by these monumental calculations. They provide the essential context, the possible histories, against which we can interpret the faint signals from the dawn. In this way, the supercomputer and the telescope work in perfect tandem. One builds possible pasts from the laws of physics, the other sifts through the real past for confirming evidence. Together, they are slowly turning the grand, theoretical story of the first stars into a documented chapter of cosmic history, allowing us to witness, through a digital lens, the very moments our material world was born. This grand cosmic cycle is not a distant abstraction. It is the story of your own physical existence. Every atom of carbon that forms the intricate molecules in your cells, every atom of iron that carries oxygen in your red blood cells, every atom of calcium that strengthens your bones, with the sole exception of the primordial hydrogen formed in the Big Bang, was forged in the heart of a star that died long before our solar system even existed. The first stars ignited the process that made this possible. They performed the initial universe-altering act of transmutation, turning the simple gases of the cosmic dawn into the raw materials for complexity. We are, in the most literal and chemical sense possible, made of stardust that they initially created and scattered across the galactic void. When you breathe in oxygen, you are inhaling the legacy of a massive star's final fusion stages. When you feel the solidity of the ground beneath your feet, you are touching elements synthesized in stellar furnaces and supernova blasts. This connection transforms the epic narrative of cosmic history from something we observe into something we embody. You are not just hearing about the first stars, you are carrying their legacy within you, a living testament to a chain of creation that began over 13 billion years ago in the brilliant, brief lives of those original giants. That cycle of stellar birth and death never truly ended. Our own sun is not a first-generation pioneer, nor even a second-generation descendant. It is a third or later-generation star, a product of this cosmic recycling process that had already been running for over 8 billion years before its birth. The cloud of gas and dust that collapsed to form our solar system was already richly seasoned with the ashes of countless stellar ancestors. Every element on Earth, from the iron in its core to the oxygen in its atmosphere, was inherited from this long legacy of stellar lives and deaths. Our sun, in its stable, middle-aged glow, is a living testament to the maturity of this galactic ecosystem, a star born from a universe that had already learned the art of complex chemistry. This grand cycle continues today all around us. Look up at the night sky, and you are witnessing every stage of the process. Brilliant, young blue stars blaze in stellar nurseries like the Orion Nebula, their fierce ultraviolet light sculpting the gas clouds from which they were born. Older, stable stars like our sun steadily fuse hydrogen into helium in their cores, and in the final act, aging red giants shed their outer layers in gentle stellar winds, returning carbon and other processed elements to space. Even the most dramatic finales are still occurring. While rare in our galactic neighborhood, supernova explosions happen regularly across the cosmos, each one a sudden, brilliant infusion of newly forged heavy elements into the interstellar medium. The galaxy is not a static museum, it is a dynamic, living factory. The interstellar medium, that thin gas between the stars, is constantly being stirred and enriched by these events. Stellar winds act like gentle cosmic breezes, carrying away processed material. Supernova are the violent storms, churning and mixing the galactic gas with the products of explosive nucleosynthesis. This ongoing enrichment means the galaxy's chemistry is still evolving. Stars forming today are born from material that is more metal-rich than the cloud that formed our sun 5 billion years ago. Future generations of stars and the planets that may form around them will start with an even richer chemical inheritance. The process the first stars ignited is self-perpetuating and self-amplifying. Each turn of the cycle produces more heavy elements, more dust, and more complex molecules, paving the way for increasingly diverse and intricate cosmic structures. It is a slow, majestic engine of change, operating on timescales of millions and billions of years. The galaxy is, in a very real sense, growing up, becoming more chemically complex and mature with each stellar generation. The profound implication is that we are not at the end of this story, but living within an ongoing chapter. The atoms that make up our world are not relics of a finished process. They are temporary participants in an endless cosmic dance. The oxygen you breathe may one day, in the distant future, be part of a comet in another star system, or a mineral on a planet orbiting a star that has not yet ignited. The iron in the ground beneath you might eventually be recycled through the mantle of a tectonically active world, or even be swept up into a future generation star. The first stars broke the universe's chemical symmetry and set this great wheel in motion. Today, that wheel continues to turn, driven by the lives and deaths of stars, quietly building the potential for futures we can scarcely imagine. Their journey was the universe's first and most critical act of creation. From a silent, featureless sea of simple gas, the first stars emerged as cosmic pioneers. They did more than just pierce the darkness, they fundamentally rewrote the chemical rules of existence. Through the furious nuclear fusion in their brilliant, brief lives, they forged the very first heavy elements, transforming hydrogen and helium into carbon, oxygen, and iron. And in their spectacular, explosive deaths, they became the universe's ultimate dispersers, seeding the void with the raw materials for everything to come. That initial act of stellar alchemy set in motion an irreversible chain of events. The enriched gas cooled efficiently, allowing for smaller, more diverse stars like our Sun. It formed dust grains which enabled the formation of rocky planets. It provided the atomic building blocks that, over billions of years, would link together into the organic chemistry that underpins life itself. Every mountain, every ocean, every living thing is a testament to that ancient, transformative era. We are the direct beneficiaries of that first cosmic revolution. The atoms that construct our world and our bodies are recycled stardust, a legacy handed down across generations of stellar lives and deaths. Our story does not begin on Earth, but in the hearts of those vanished giants. As we stand here today, looking up at a night sky filled with their descendants, we are witnessing an ongoing process. The cycle they ignited continues, with stars being born, living, and dying, slowly enriching the galaxy further. Our understanding of this profound narrative is still unfolding. The next generation of observatories, peering ever deeper into the infrared dawn, promises to bring those first luminous architects into clearer view. What new details of their lives and deaths will we uncover? How will their individual stories refine our own cosmic origin tale? The quest to witness the dawn of chemistry is ultimately a quest to understand our own deepest ancestry.